Hey guys, my name is Shreyas and welcome to Simple Chemistry. In this video we're going to be talking about electron distribution exceptions. Now if you've learned this already in class, you might have noticed that in one of the previous lessons when I talked about the electron configuration for gold, it was actually wrong. And I did that on purpose because I wanted to talk about how this is this comes into play. Okay, so we're going to be taking a look at that. So some atoms, specifically copper and chromium, exhibit exceptions in their electron distribution. Okay, so let's go ahead and look at this. Let's first write the electron distribution for copper. So in order to do that, we need to go ahead and write the electron configuration. Copper is right here, so the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So let me write that down. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, and then 4d9. Okay, 3d9, sorry. Okay, so from here, let's go ahead and look at the electron configuration in these sublevels. So I'm not going to write the complete electron distribution. I'm not going to write it for all of this. I'm just going to write the electron distribution for these sublevels. Okay, so we have one 4s orbital, and then we have 5 3d orbitals. 1, 2, 3, 4, 5. And then we know this sublevel has this orbital will have 2 electrons, and this one will have 9. So 1, 2, 3, 4, 5, following Hund's rule, 6, 7, 8, 9. So what this is saying is atoms prefer half-filled sublevels over partially filled sublevels. So if you look here, this sublevel right here, let me go ahead and highlight it. This sublevel right here has a full, completely filled sublevel, meaning that the electrons are completely filled. Here we have a partially filled sublevel because all these orbitals here are all completely filled, but then this one is just left alone. So it's actually partially filled because this last orbital right here has only 1 electron. So what we can do is we can take this electron over here and move it here, because this is actually preferred. So atoms prefer half-filled sublevels over partially filled sublevels. So now instead of having what we originally had, which was a filled sublevel and a partially filled sublevel, we have a half-filled sublevel because there's just half, and then we have a completely filled sublevel, which is actually more stable. Okay, the reasons for that I don't really want to get into it, but just know this. Okay, so the actual electron distribution, electron configuration, this is like correct electron distribution, but the actual correct electron configuration would be 4s1 3d10. Okay, this is not the excited state. Okay, we're not talking about an excited state here. This is actually just preferred. Okay, and you can imagine now we talked about how my example for gold was wrong. It happens to all these atoms within this this column here: copper, silver, gold, and that is some radioactive thing. Because basically just copper, silver, and gold all exhibit this. So we talked about so for gold, for example, let me go ahead and erase this. For gold, let's just write the neon gas, not the neon, what I'm saying, noble gas electron configuration. So that'd be xenon, and then 1, 2, 3, 4, 5, 6s2, 4f14, 6s2, 4f14, and 5d9. Right, so 6s2. So what's going to happen is the same thing. Just like how we saw one of the electrons from the s orbital pop into the d orbital, it's going to happen here too. So actually, even though in the previous video we said this is the electron configuration, the correct electron configuration is actually 6s1, 4f14, 5d10. Okay, this is actually the correct electron configuration, so don't make this mistake. Same thing here. With silver, you can imagine it would just be, you get over here, we're at 5s2, 4d9, it'll turn into 5s1, 4d10. You just move an electron from the s orbital into the d orbital. Okay, now let's look at chromium. So for chromium, chromium starts to do a slightly similar thing. So let's look first, write the electron configuration for chromium. So that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and chromium 3d9. Wait, make sure. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. Did I get that? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, right? 1, 2, 3, 4. So let's go ahead and look at the electron distribution to better understand this. We can just take it here. So that would be, we have 1 4s orbital, and then we have 5, 1, 2, 3, 4, 5, 3d orbitals. And the electrons will be distributed like this. So 2 here, and then 1, 2, 3, 4. So here we have a filled sublevel here for the 4s, and then we also have a partially filled sublevel because this orbital does not have any electrons. Okay, so what's going to happen is that this electron right here is going to move over here. So one of the electrons in the 4s orbital will come to this 3d orbital, and now we have all of these are half-filled sublevels. Okay, and this is actually preferred. So our electron configuration is going to change from 4s2 3d4 to 4s1 3d5. Okay, and this is actually the correct electron configuration. Same things would happen for everything in the, something similar would happen for these elements, molybdenum and tungsten. So let's look for example, let's just look at tungsten. The electron configuration there would be the electron configuration there would be, let's just write the noble gas configuration, so that would be xenon, and then xenon 6s2, 4f14, and then so 6s2, 4f14, and then 5d4. So something similar is going to happen where we take one of the electrons in the s orbital and move it to the d orbital. So the correct electron configuration would actually be 6s1 and then 5d5. Okay. So that's basically the electron distributions that you need to know. I don't think you'll ever run across having to mention the electron distributions for these. The only real ones are copper and chromium, but just make sure you know these. They're pretty simple, and I hope that this helps you. Electron distribution exceptions are as simple as that.